Alright, so we're talking with section 3.3 on the properties of logarithms. We've already talked about the basic properties of logarithms and what they are kind of at their core. Remember all the relations that we have. We can't take the log of a negative number. The base can't be a negative number or 1. We can't take the log of a 0, and there's, all those things we need to keep in mind as we're talking about these things, because those are things that are going to throw in when we integrate x's and things like that into our log expressions. It's going to introduce domain issues that we have to make sure that we keep in mind. All right, the first property we're going to talk about is the product rule. And it says, let b, m, and n be positive real numbers with b not equaling 1. In that case, the log base b of m times n is equal to the log base b of m plus the log base b of n. So what we can do is we can take this property here, this product, the log of a product is equal to the sum of the logs of each one of those factors. Now you'll notice here b, b, and b, all the bases of these logs are the same. Now this is in the same way going to work with natural log and all those things as well. So that's the situation we're dealing with. As long as the base stays consistent all the way across, we have this product that we can do. And this is a way that and this one works. You need to keep in mind this one will work either way. You can take a log of a product and break it into the sum of the logarithms, or you can take the sum of the logarithms and make it into a more concise and smaller version of a log. So this is a property that goes both ways. Alright, so use the product rule to expand each logarithmic expression. Now, this is one of the reasons and one of the ways that this property became really important. And this makes sense if you really think about it, because if we're doing the log base b of m, we're finding what power b has to be raised to equal m, right? And the same thing with the n. What power does b have to be raised to get n? So that both of these would be powers. And what do we do with powers when we're multiplying? Well, we add them. That's why the product rule works here. The product of the log of a product is equal to the sum of the individual logarithms, because this is going to find the power b would have to be raised to for m. This is going to find the power that b would have to be raised to n. And if we multiply these together, then that power will be put together and added. And another way that this was used in the past is the fact that they didn't have calculators, so they would have log tables. And you could actually break this thing down into small log expressions, or a sum of a bunch of small log expressions. And you could use the log table and you could actually find out what the answer is. Whereas we can do the log base 4 of 35 and find it with a calculator pretty easy. They didn't have that option. So if we're going to use the product rule to expand this, remember we're going to have the log base stays the same of the first part of our product plus the log base 4 of the second part of our product. And then, like I said, in the days before they had calculators and things like that, they could possibly have a log base 4 of 7, a log base 4 table, and they would have all those decimals, so they'd write the decimal down for this one, write the decimal down for this one, and they could add them. Now, this one over here, this makes it a little easier. This is a common log, remember. No base means it's understood to be a base of 10. So we have the common log of 10 plus the common log of x. Now, what is the log base 10 of 10? Well, that's just 1. So we end up with 1 plus log of x. If you can simplify it like that, definitely simplify it. You can't really simplify this without a calculator. In that case, you can leave it just like it is. Alright, I want you guys to pause the video and try these two, expand them, and see what you get. And I'm going to show you the answer for you to check in 3, 2. Alright, so here are the answers. For part A, log base 6 of 7 plus log base 6 of 11. None of those are really easy to simplify down or to find the value for, so we leave it like it is. Over here we break it up as log of the product, log of 100 plus log of x. Well, the log of 100, remember this is once again my common base. It's a common log, so it's a base 10. 10 to what power gives me 100? That would be 2. So that would simplify down to 2 plus log x. Alright, now just like we have the product rule, we also have the quotient rule. So same setup here. Let b, m, and n be positive real numbers with b not equaling 1. The log base b of m divided by n is equal to the log base b of m minus the log base b of n. So where we're dividing here, same thing. Remember, we're finding the log base b of m. We're finding what power b would have to be raised to get m. Same thing, log base b of n. And when we divide those, what do we do with our powers? We subtract them. So the logarithm of a quotient is the difference of the logarithms. Alright, so let's go ahead and work this one. We've got log base 7 of 19 over x. So we've got the log base 7 of 19 minus the log base 7 of x. And log base 7 of 19 is not something we can really simplify, so we can leave it just like it is. Now over here we've got the natural log. So we have the natural log of e to the third minus the natural log of 7. Remember, this is a log base e, and if the base and the base of the exponential match, then they cancel each other out. So that means we're going to have 3 minus the natural log of 7. Once again, there's one of those powers, one of those properties that we learn that you need to make sure that you remember, because they make simplifying things much, much, much easier. Alright, I want you guys to try these two, pause the video, work them out, and then you can come back and check your answers, and I'll show you the answers in 3, 2, 1. Alright, so here's the answers. When we break this one down right here, log base 8 of 23 over x becomes log base 8 of 23. Top first always. Minus log base 8 of the bottom, x. Same thing over here, natural log of e to the fifth minus natural log of 11. And once again, same way we did with this problem right here. Remember, this is a log base e, and if the base of the exponent and the base of the exponential that you're taking the log of match, and those things cancel out and leave us with just 5 minus the natural log of x. Sorry, 5 minus the natural log of 11. Alright, and then we have the power rule, and this one comes in very, very handy. Let b and m be positive real numbers with b not equaling 1, and let p be any real number. The log base b of m to the p power is equal to p times the log base b of m. Now, once again, it goes back to what we know about powers. Remember, if we're doing the log base b of m, we're finding what power I have to raise b to get m. So the log finds a power. Well, the p is a power. And what would you do if you were raising something to a power is you multiply exponents. So that's why this p can move out front and multiply because it's already a power. That's an exponent. And when we do the log base b of m, we're going to find another exponent and we'd multiply them together. So the logarithm of any number with an exponent is the product of the exponent and the logarithm of that base number. So use the power rule to expand each one of these. So with this one, we're just going to move the 4 out front. So we end up with 4 times the log base 5 of 7. Since we can't simplify that log expression anymore, we stop there. Now here we want to rewrite this thing. Natural log, what's another way of writing the square root of x with an exponent? Well, it's going to be x to the 1/2. Then we can move that power out front. So this is going to be 1/2 the natural log of x. And then what do we know about the log base 4x to the 5th? Well, we can move that 5 out front, and we're going to get 5 times the common log of 4x. Now at that point, though, we can also take and we can, it doesn't specifically say, it just says use the power rule, but we can expand this even more if we need to. And we're going to have 5, and we have a product right here. So we could actually do this as log of 4 plus log of x. And you can distribute that 5 through if you want to. 5 log of 4 plus 5 log of x. But they just said power rule, so that's where we're going to stop. We just moved the power out front. But remember, if it says expand it completely, you want to expand that. Do not leave that like it is if it says expand completely. And you could get 5 log of 4 plus 5 common logs plus not equals of x. So this would be expanded completely right here. Just use the power rule, that would have been far enough. If it says specifically just use the power rule. But it said use the power rule, and yeah, it could be kind of understood to expand it all the way. So when in doubt, expand it all the way. All right, I want you guys to try these 3. Pause the video, give them a try, and then come back and check your answers. And I'll show you the answer in 3, 2, 1. All right, so here are your answers. You can move that exponent out front and get 9 log base 6 of 3. Guys, be real careful. 3 and 6 have that half relationship, but do not think that log base 6 of 3 is 1/2. It's not. Remember, if we're doing a power of 1/2, that means you're taking the square root. Is the square root of 6 3? No, it's not. So be real careful. Don't read too much into it and don't try to do too much if it's not possible. With this, we could just rewrite that as the natural log of x to the 1/3 with that cube root there. And then bring the 1/3 out front and get 1/3 natural log of x. And then log base, or the common log of x plus 4 quantity squared, all we can do is move that 2 out. You cannot express this any simpler than that. You cannot split this up and say log base x plus log base, or common log of x plus common log of 4, because that's not a rule. We don't have a sum rule. We have a product rule. If this was 4x like it was up here, we can split it up more. Here we can't. Do not think that the product rule will allow you to split this into 2 logs. That's just a single log expression, and it has to be left like it is. There's not a rule to expand that. So don't get the product rule and some rule that doesn't exist mixed up. Make sure you remember we have to have a product in the log to expand it to a sum of logarithms, not the log of a sum to the log of a product. That doesn't work. All right, so here's just a review of the properties for expanding the logarithm expressions. We got the product rule, quotient rule and the power rule. And once again, just from that last one, remember, it has to be the log of a product, and it's expanded into the sum of two logs. You can't have the log of a sum and expand that in any way. And the same thing with our quotient here. You can't have the log of a difference and change that into something else. It has to be simplified as it is. All right, so use the logarithmic properties to expand each one of these expressions as much as possible. So let's go ahead and work through one of these. And I'm going to move this up just a touch. We can still see everything though. So for A, it may take a step or two to get everything squared away. First of all, you need to identify what you have. So right here, what's the first thing we have is we have the log of a product. So the log of a product, we can actually break down into the sum of two logs. So we're going to have log base b of x squared plus log base b of the square root of y. Now, we're not done. We still have powers. Then we can use our power rule. So the 2 I'm going to move out front. So you get 2 log base b of x plus, and remember y, the square root of y is nothing more than y to the 1/2. So we can go ahead and think about that as y to the 1/2 and move that 1/2 out front. Plus 1/2 log base b of y. And then that is expanded as much as you're able. All right, so let's do b. Sorry about that. So we've got log base 6 of the cube root of x over 36y to the 4th. Now we got quite a bit of stuff to do here, but the very first thing we need to deal with is our quotient. So we're going to have log base 6 of the top, the cube root, actually let's go ahead and rewrite it. Remember, a cube root of x is nothing more than x to the 1/3. And then we're going to subtract the log base 6 of the bottom, which is 36y to the 4th. All right, so we still have a product right here, so we're going to have to deal with that as well. And we also have a power here. We can go ahead and deal with it and be done with that first one. And minus, and I'm going to put parentheses because we're subtracting this thing. And when we break this thing right here down, we need to put that in the parentheses there. So we're going to get the log base 6 of the first part of our product, 36, plus the log base 6 of y to the 4th. Now at this point you can distribute that negative through or whatever. I'm fine with you leaving the parentheses, but I'm going to go ahead and distribute the negative through. So 1/3 log base 6 of x is just kind of tagging along. When I distribute this through, both of these terms are going to be negative. So minus, now what power would I raise 6 to get 36? Well, that'd be the second power. So that right there simplifies down to 2. 6 squared gives me 36, so 2 is your exponent. And then the minus times this makes this a minus. And what do I have to do here? All I have left is to do the power rule, which moves that 4 out front. And we have log base 6 of y. And then we're finished there. So we have no powers, we have no products in logs, we have no quotients in logs. And once we've got to that point, we've simplified it as much as possible. All right, I want you guys to pause the video and try these two. expand them as much as possible. Pause the video, give them a try, and then I'll show you the answer in 3, 2, 1. Alright, so here are the answers. Check your work. Remember, you've got it simplified when you have no more powers in your logs and you have no more products or quotients in your logs. That's expanded completely. Alright, now in the same way that those rules and properties are used to expand, you can also use them in the other direction, as we talked about, to condense or to get everything into one log expression. And these are just nothing more than those other ones going backwards. So if you want to go back and draw the little arrows under these equals, just remember it goes both ways. You don't have to rewrite these rules all over again. Alright, so let's write these as a single logarithm. We're just kind of working backwards from what we were doing before. So if we've got the log base 4 of 2 plus the log base 4 of 32, we can go ahead and understand that that's going to be a product, rule, reversal, because we've got the sum of two logs that have the same base. Log base 4, log base 4. So this is nothing more than the log base 4 of 2 times 32, which is 64. Well, 4 raised to the third power gives us 64, so that's 3. Now with this one, it's a little different. We have the common log of 4x minus 3 minus the common log of x. Well, it's going to be the quotient rule, and we're going to have the common log of 4x minus 3 divided by x. And that's all that there is to it. Just take them and put them back together. This is the log of the first. This is what you're taking the log of in the first one. That's on top. This is what's on the bottom. Alright, you guys try these two. See what you can come up with. Simplify as much as possible. And I'll pause the video and show you the answer. Sorry, you pause the video, work it out, and I'll show you the answers in 3, 2, 1. Alright, so here are your answers. The first one's going to simplify down to the common log of 100, which is 2. The second one is the common log of 7x plus 6 over x. Guys, you're probably wondering, do you have to put the parentheses around this? I would, always. For two reasons. One is because it's going to make for better notation. The second is, well, I know how you guys write, and it stinks for the most part. And you're just as likely to have something written with log of 7x plus 6, and then you'll draw the line in here and put over x. That is completely different. These are not equal. So that's why you should have the parentheses to separate and define what you're taking the common log of. It's just good practice, good notation, and it keeps you from being misunderstood or making the wrong statement. Alright, so more of our problems here, and these are a little more complicated than the ones we were just dealing with. Not too bad. So let's look at A. First thing we want to do is we want to get rid of those powers, get rid of the coefficients out front. We're going to we're going to use the power rule backwards and make the powers go, or the coefficients go away. So 1/2 becomes a power of x. The 4 becomes a power of x minus 1. And at that point, what can we do? Well, we've still got our sum here, so we can combine these into one log. And we can simplify while we're at it. X to the 1/2 is the square root of x, and x minus 1 to the 4th, well, is just x minus 1 to the 4th. And you can put parentheses down or brackets, either one. All right, so B, let's go ahead and move up here for B. B's not that bad. The only thing we really got to worry about is the power here. So this is going to be natural log of x plus 7 to the 3rd power minus the natural log of x. And then we can combine this into one natural log expression, x plus 7 to the 3rd power over x. Because of the minus, it's a quotient problem. All right, and then C, we've got 4 log base b of x minus 2 log base b of 6 minus 1/2 log base b of y. And once again, remember, if these logs are not all the same base, we cannot do this stuff. You need to understand, if those bases are not the same, we cannot use these rules. These rules only apply for logs of the same base. Now, all these are the same base, so we can go through and let's remove the coefficients first, reverse the power rule. We're going to have log base b of x to the 4th minus log base b of 6 squared minus log base b of y to the 1/2 power. Now, here's where there's a little trick that comes in, and I want to kind of go back just a bit. And I want you to see something. If I can remember where it is. Okay, right here. Notice this. Both of these terms are minus. And where did that come from? Well, that came from the distributive property of this negative through. If you have multiple terms that are minus, you need to factor that negative out. And you'll see why in just a second. So let's go back to where we were. So if I factor the negative out of these two, I'm going to have a log base b of x to the 4th minus, and then brackets or parentheses, and this one's going to be positive and this one's going to be positive. So log base b of 36 plus log base b of the square root of y. All right, so now hopefully you can see what we're doing. We've got a quotient between this and this, but I need to combine this first. So I'm going to move this up here. We're going to have a log base b of x to the 4th minus, when I combine these, I'm going to get the log base b of 36 square roots of y. So once I put those two together as the product, now I can do my quotient rule reversal. And that's going to be log base b of x to the 4th on top over 36 times the square root of y on the bottom. All right, so that's how you do these. Just basic properties to use, nothing big. And we'll get to work on those in some in class. All right, the last thing we need to talk about is the change of base property, or the change of base formula. For any logarithmic bases a and b, and any positive number m, the log base b of m can be expressed as the log base a of m divided by the log base a of b. Now, you're noticing here, or if you're paying attention, you're noticing that we're just swapping a log base b with two log base a's. And you were like, well, why in the world would you want to do that? Well, the common log that was a log that they had tables and tables and tables of values. The natural log, ln, that's another one that they had tables and tables and tables and values of, so they could actually calculate those without a calculator. And that's how they did all the calculations that they would need to do. So, for instance, if you wanted to find the log base 2 of 6, back before calculators were around, you could actually go to a log table. You could either use the common log or the natural log. But what you would do, I'm going to change it to natural logs. You do the natural log of 6 divided by the natural log of 2. Well, then you would go and you would actually find out what the natural log of 6 was. Or you could even do this one step better, and you could break it down even more, because you didn't have non-prime values of logs. So you would take this natural log of 6 and you'd think about that 6 as 2 times 3. And then guess what you'd use? You'd use the product rule, and you would have the natural log of 2 plus the natural log of 3 over the natural log of 2. Now, before you start thinking, hey, well, we can just cancel those out, you can't actually cancel those out. That has to divide into both parts. But what you would do, you could divide the natural log into both parts, and you would get 1 plus the natural log of 3 divided by the natural log of 2. And this is just decimals that you could actually do long division with. You would go and you would find the value for the natural log of 3 on your table and the value for the natural log of 2 on your table in your tables, and you would just divide those decimals and then add that to 1, and you would have the log base 2 of 6. So we actually have saved a lot of work with our calculators, but this is how the calculator does it, by the way. That's actually how the calculator would do it. But you still need to know these rules and these properties, because that's another way to algebraically manipulate things that don't just have numbers in it. Because you're not always going to have log base 2 of 6. You might have log base 2 of x. And in that case, what do we know? That's going to be an x. That's not going to change. It's going to be the natural log of x. And now we might be able to do something with it, or a little more. We're going to learn more about what we can do with it later in the chapter. All right, and that change of base formula applies to both the common log and the natural log. You can use either one. These are the common ones that are the ones that are typically used to transform a log base b of m into some other base. It's usually transformed to either the common log, base 10, or the natural log, base e, just because those are widely used logarithms. All right, so let's use common logarithms to evaluate the log base 5 of 140. All right, so if we're going to use common logs, we're using the log base 5 of 140, and we're using common logs, so log base 10s. So we've got the common log of 140 divided by the common log of 5, and then you just put both of those in your calculator. Now the common log of 140 is 2.146128, and the log of 5, the common log of 5, is 0.69897. And when we do that division, we get 3.0704 Now, typically, you're only going to have to go to like 3 decimal places on these. And remember, what is this we've actually found? We're asking what power would I raise 5 to get 140? Well, we know that 5 squared is 25. And we know that 5 to the 3rd power is 125. And we know that 5 to the 4th power is 625. So it makes sense that it's going to be a lot closer to 3 than it would be to 4. And hence, there's the answer that we get. So guys, don't blindly believe the calculator or anything like that. Go back and think through your integer powers and see if that number makes sense. 5 to the 3.070415 power is going to equal 140, and that makes sense looking at this, what we've got right here. Alright, so I want you guys to pause the video, grab a calculator, and try this and see what you can come up with. And I'm going to show you the answer in 3, 2, 1. Alright, so here's the answer. We're going to take our log base 7 of 2506, break that down using common logs, using the change of base formula, and we're going to have common log of 2506 divided by the common log of 7. Common log of 2506 is 3.39898, and common log of 7, 0.845098. When we divide that out, we get 4.0219. Now let's go ahead and look and see, does this make sense? Well, if we have 7 to the 2nd power, 7 squared is 49. 7 to the 3rd power is 343. 7 to the 4th power is 2401. And if we multiply that times 7 again to get 7 to the 5th, we have 16,807. So there with the 2506, it once again is going to be closer to 4 than it would be to 5 power-wise. So that makes sense. Now, guys, you don't have to always do this, but you should always think about how that actually works, because that's going to increase your understanding of it. And if you can see that, hey, that makes sense, or figure out that, hey, that makes sense because 7 to the 4th is 2401, but 7 to the 5th is 16,000 something. 2504, the log base 7 should be raised to a power that's much closer than 4 than it is to 5 to get 2506. And we find that out with our calculations here.